Okay, so today we're going to take our everything we learned about unit conversions and apply it to chemical reactions and equations. So just a reminder, some of the parts of our equations for our reactions, we have our reactants on the left. On the right, we have our products. The large numbers in front are called the coefficients. We have molecules, or we can call them formula units. I usually call them molecules. On the other side, we also have mercury here as a molecule and oxygen as a molecule. The small number is the subscript, and it tells you how many elements or atoms of that element are in a molecule, and then we can include the physical state if we want as well. So in this case, this reaction, remember we have to have our reactions balanced, and this reaction is not balanced because right now it shows we have 2 mercuries and 2 oxygens, and on the right with our products we do have 2 oxygens, but we're missing 2 mercuries, so we need to add a 2 here. Okay, so having balanced reactions is very important. So now we're going to apply this our stoichiometry, what we've learned, to chemistry. So we can think about our reaction just like we would our recipe. So for instance, if we're thinking about this recipe to make peanut butter cookies, and we have a cup of peanut butter, a cup of sugar, and 1 egg makes 12 cookies, we could kind of think about writing it in the same type of format as our reaction. So we could think about, we have peanut butter, we have sugar, we have eggs that we are all adding together, so those are our reactants, and then our product is going to be the cookies. And then we can use our coefficient, to show how much of each of those things we're using. So we have 1 cup of peanut butter, 1 cup of sugar, 1 egg. But in chemistry, if we have a 1, we just assume that it's there. So we don't have to actually show those ones, but we do need to show that there's 12 cookies being produced. So we have 12 here. So one thing that would also be helpful is to show that we can balance reactions. So in this case, we can't quite balance it because we've used different letters for cookies and for the ingredients. So it would be better if we could show, instead of having C for cookies, we could show that 1 cookie is made of peanut butter, sugar, and eggs, and kind of put it all together in a compound. So try to take that information to make a reaction for grilled cheese sandwiches using this. So you can pause the video and try to come up with your own reaction for grilled cheese sandwiches using this recipe. So pause the video. Okay, so what you could do for this is you could show that you have 4 pieces of bread plus 3 tablespoons of butter plus 2 slices of cheese, and all of that yields, remember our arrow means yield, we're making 2 grilled cheese sandwiches. And we don't want to write grilled cheese sandwich because we want to show that our equation can be balanced and we have the same, it's following the law of conservation of matter. We have the same amount of matter in the same atoms as we had before. So 1 sandwich, we could think about 1 sandwich is a unit. So and we're making 2 of them. So 1 sandwich is going to have bread, but it's going to have 2 pieces of bread. For butter, we said we have 3 tablespoons for 2 sandwiches. So we're going to have butter, but we're only going to use 1.5 tablespoons. And then we have cheese, but we're only using 1 slice of cheese per sandwich. So this is the formula then we could use for a grilled cheese sandwich, and we're making 2 of them. So this is how you can kind of think about our reactions, is just another way of writing our recipe. And remember, we can use our recipe to convert from amounts of things. If I want to use 6 slices of bread, we can then use our stoichiometry to convert and cancel bread, because we know 4 bread equals 2 sandwiches. So we can use that information to convert. So we can use our recipe, in our case for reactions, it's our balanced chemical equation, to convert from moles of one molecule to moles of a different molecule. And it's important that it's in moles. So here is an equation, and so the first thing, though, notice is that it needs to be a balanced chemical equation. So the first thing we need to do is balance this chemical equation. So you can pause the video and balance it and see if you get the right answer. So pause the video. Okay, after you balance this, you should get 2, 1, 2 for your coefficients. So we have on the left side, we have 2 nitrogen, right side 2 nitrogen. Left side we have 2 plus 2, so 4 oxygen, and 2 times 2, 4 oxygen. So it's now balanced. So we wrote this equation, but another way of thinking of this is as a recipe where we have 2 moles of nitrogen monoxide, which is this, will react with 1 mole of oxygen, because we have a 1 here, and if we use 2 moles and 1 moles, we're going to make and produce 2 moles of nitrogen dioxide, so 2 moles of our NO2. So this is in word form what this equation is telling us. It's just telling us the recipe for NO2. And we can use this proportion to figure out how much if we want to decrease or increase the amount that we're making. Okay, so this is the same reaction, so I'm just going to put our coefficients up here. We had a 2, we had a 1, and oops, we had a 2. Okay, so our question for this would be how many moles of O2, or 3.6 moles of O2 will make how much NO2? So here we're starting with the number we're given. We're starting with 3.6 moles of O2. And so we're converting, so we need to draw our table so we can convert. And remember, if we want to convert, we want the units that are diagonal from it to be the same so it can cancel. So we need moles of oxygen, and we're wanting to convert to moles of something else, and that is moles of NO2. So we've set this up just like we would any other way for a unit conversion. But now to know what numbers we go in, we have to look at our recipe. So that means we're looking at our reaction. And we see that for every 1 mole of O2, we're making 2 moles of NO2. So we have a 1 that's going here for our O2 because that's what coefficient's in front of it. And for NO2, we have a 2. So you can see that our moles of O2 units are going to cancel. So we're left with 3.6 times 2. So you can do that and you can find that it's 7.2. And we want to double check our sig figs. We started with 2, we ended with 2. And notice that we don't use the coefficients for sig figs to determine the number of sig figs because they have an infinite number, because this is exactly 2, exactly 1, and exactly 2. And then the last thing we need is our units. So we have 7.2 and we're left with moles of NO2. So these are very similar to the types of things we've done before. We're just now using our reaction as our recipe. So you can pause the video and try this one on your own. So I'm going to scoot this down a little bit so I can get a little more space to work. Okay, so this time we're wanting to form 4.67 moles of NO2. We're kind of working backwards, saying if I want to make 20 cookies, how much butter do I need type of idea. So we're starting with 4.6 moles of NO2. And notice that I write the molecule and I write that it's in moles because that will become important later. We're going to draw our chart. We want that to cancel, so we have moles of NO2. And we're going to moles of nitrogen monoxide, so moles of NO. And then we look up at our equation again. Up here, we see that to make 2 moles of NO2, we need 2 moles of NO. So we have a 2 and a 2, both of those numbers coming from our balanced equation up here. Our units cancel, and so we're left with 4.67 times 2 divided by 2. And you may notice right off the bat that these two 2's will cancel. If not, you can put it in your calculator and you'll notice that the number you get is 4.67. And we'll double check our sig figs. It has 3, so does this number, and our unit is moles of nitrogen monoxide. Okay, so we're going to go through and practice several more of these. So I encourage you to pause the video after I've given you the questions so that you can practice it and then check your answer. So here's one, and I've balanced this equation for you so you know that you have iron 3 oxide plus 1 mole of iron 3 oxide plus 3 moles of hydrogen are going to yield 2 moles of iron and 3 moles of water. Okay, so here's your first question. You can pause the video and try it on your own. Okay, what we're going to do is we're going to put 25 moles of iron 3 oxide. And then we'll draw our unit conversion chart. We want that to cancel, so we'll put moles of iron 3 oxide on the bottom. Oops. And we're wanting how much iron is made, so we'll put that on top because that's where we're going. And this is moles of iron. And then we'll look up at our equation. We see that to make 2 moles of iron, we need 1 mole of iron 3 oxide. So if we do 25 times 2 divided by 1, we're going to get 50 moles of iron, because remember that these units cancel. And we need to check sig figs. So this number has 2 sig figs, and our number right now only has 1 because this 0 is not significant. So we could add a decimal place to show that it's significant, or you could write it as 5.0 times 10 to the first power. Either way would show that. Okay, so now here's another one. You can pause the video and try this on your own. So we're going to start with 30 moles of iron. Draw our chart. We're going to go from moles of iron, and it's wanting to know how many moles of hydrogen. So remember, hydrogen is going to be H2 because it's a diatomic element. It's in My Brother Hongcliffe, so it's going to have a 2 as a subscript. So we look up here at our coefficients. We have 3 moles of hydrogen. We have 2 moles to make 2 moles of iron. So we're going to do 30 times 3 divided by 2 is 45. And this is moles of hydrogen because our moles of iron both canceled. So check sig figs. This number only has 1 sig fig because 0 is not significant, and our number right now has 2. So the way we would write this, instead of 45, we would only have this 1 digit that's significant. So that means we need to use a 0 placeholder, and because this is a 5, we're going to round this up to a 5 and then put 0 as our placeholder. So the 45 would round up to 50 moles of hydrogen. Okay, so here's some more to practice. So this one's already balanced for you. So I would pause the video. It tells you that octane is CaH18. So we have 2 moles of octane plus 25 moles of oxygen yields 16 moles of carbon dioxide plus 18 moles of water. So you can try to figure out how much oxygen is going to be needed to make 4 moles, or to react with 4 moles of octane. So pause the video. Okay, we're going to start with 4 moles of octane. And then we'll draw our chart. We'll put moles, oops, octane, and we're going to moles of oxygen, so that's going to go on the top. We look at our equation, and we see that 25 moles of oxygen are needed, and 2 moles of octane are needed. So now our moles of everything cancel. So we're left with 4 times 25 divided by 2, which is 50. We only have 1 sig fig because we're using 4. So we will still write that as 50 moles of O2. Okay, so you can try this next one. Pause the video and try it on your own. In this one, we're starting with 1 mole of octane. We will draw our chart. We need to write moles of octane. Can't see what I'm doing. And this one's wanting to know how many moles of CO2. So we'll write moles of CO2. go back up to our equation, we see that we have 2 moles of octane needed to make 16 moles of CO2. So 1 times 16 divided by 2 is going to be 8. And that's the right number of sig figs. We only have 1 here. So 8 moles of CO2 because these units cancel. Okay, here's another one. You can pause the video again. So this time we're starting with 6 moles of octane. So we'll draw our chart. We need to convert moles of octane, so that goes on the bottom. And it wants to know how much water is going to be produced. So we're going to put moles of water on the top. We look at our equation. We have 2 moles of octane needed, and if we do that, we will make 18 moles of water. So 6 times 18 divided by 2. 54. But notice we only have 1 sig fig, so we're actually going to round this to 50 moles of H2O. Because our units here cancel. And that's what we're left with. Okay, we'll try another one. This one I just moved the equation down here so you can have it. So you can pause the video. It actually has 2 parts of the question. First, figure out how much O2 is made, and then figure out how much O2 is needed, and then how much octane is needed. Okay, so for the first one, we're going to start with 8 moles of the CO2. We're going to draw our chart. We want moles of CO2 to cancel, so that's going to go on the bottom, and we're wanting to know how much oxygen is made. So now we're going to go back to our equation. CO2 has 16, oxygen has 25. So our moles of CO2 cancel. We're left with moles of oxygen. We have to do 8 times 25 divided by 16 to give us 12.5. However, our 8 only has 1 sig fig, so we're going to round this to 10 moles of oxygen. The second part of the question is asking something very similar. It's just now saying instead of going to oxygen, we're going to go to octane. So for the most part, I'm just going to copy this because it is basically the same question. Instead of going to oxygen, we are now going to go to octane. So instead of putting 25 up here and moles of O2, we are now converting this to moles of octane. So we look up, it's still 16 for our CO2, but octane, we only have 2. So now we do 8 times 2 divided by 16, which is actually only 1, which has the right number of sig figs, moles of octane. So we can try one more. Notice that this one tells you it's unbalanced equation. So take a minute and pause the video so that you can balance the equation. So for this one to balance, we have iron, we have oxygen, we have carbon. Right now we have 2 iron on the left, we have 1 iron on the right, we have 3 plus 1, so altogether we have 4 iron on the left, or oxygen, we have 2 oxygen on the right, on the left we have 1 carbon, and on the right we have 1 carbon. So the first thing we notice that we want to do is we want to leave oxygen for last because there's this weird thing with the 2. We're going to multiply this iron by 2. So we'll put a coefficient here. So now our ions are balanced. But notice here we have our oxygen messed up. And so we have more on the left, so we're going to try multiplying over here by 2 to give us 4 oxygen. However, if we do that, it also multiplies our carbon. So now our carbon has 2, which means to fix that, we need to multiply by 2 on this side. So we'll put a 2 over here, which multiplies this by 2 as well. So now we have 5 oxygen, which messes up everything again. So notice everything's balanced except their oxygen. So we tried 2 over here, which didn't work. So let's try a 3. So now we have 6. For our oxygen, and we have 3 now for our carbon, which means we need to change this also to a 3, which affects this 2. So now we have 3 plus 3, we now have 6 oxygen, and everything should be balanced. So this one was 1, 3, 2, 3. So this one was a little bit trickier to balance, so I helped you out. Okay, so this question's wanting how many moles of iron can be made from iron oxide by the use of 18 moles of carbon monoxide in the following unbalanced equation. So we're starting with 18 moles of carbon monoxide. We want that to cancel, so we'll put moles of carbon monoxide. And we're wanting how many moles of iron. So we'll put that up here. If we look at our equation, we see that carbon monoxide, we use 3, and then it produces 2 iron. So we're going to do 18 times 2 divided by 3, which is 12 moles of iron, which has the right number of sig figs because 18 has 2, so does 12. Okay, so we have a ticket out the door. Oops, if I can find where I put it. There it is. Okay, so you have a ticket at the door. If you missed it in class, it's these 2 problems. I gave you a balanced chemical equation. Just remember that your final answer uses the right number of sig figs and you have the right units labeled.